This week we talk about logistic regression, our first step in learning how to make better decisions. And to do that, we're going to start by talking about odds. Logistic regression is a continuous version of making a decision, and it's closely related to this idea of odds. So suppose we have this set of data in this form, some collection of features or factors. So we'll also use the word factors for the features. First we're going to look at some notation, whether or not we use a capital F or a small x to denote the features or factors. We'll always use capital Y for the predicted class. Notice here, if we're using the capital X already as a variable, we're using the capital F's to denote the features. X here is the actual class, Y is the predicted class, and therefore to avoid confusion we used capital F. We use little x if capital X is not in use. So here we're calling the last column the class column, not using the capital X, and therefore we use the little x's for the features. So given this data, a decision tree node typically only is a single factor at a time, and some condition on a factor that's either true or false. Better decisions are possible if we could base them on all the factors, however. So as a function of x1 to xn. We're going to let p be the probability of true, and thus 1 minus p is the probability of false. Our goal is to derive a method for making decisions that uses all the features at each decision node. A best decision has maximal information gain. And the information gain is essentially the uncertainty before minus the uncertainty after. But what about changes from before to after? Before, we had a lower probability of correct classification, then we made a decision, and afterwards we had a higher probability of a correct classification. It's the probability of correctness that changes. And so we're going to suppose that in some abstract sense, the probability P of t is a function of time. And we're going to suppose that we make a decision at time t equals 0. The highest information gain is going to correspond to the highest rate of information change at time t equals 0. Remember, p is the probability of true, and 1 minus p is the probability of false. So if we only have two outcomes, true or false, then the entropy is negative p log base 2 of p minus 1 minus p log base 2 of 1 minus p. And p of t here is the probability that y is true. We'll often measure information gain, however, or measure information itself in nats, so we can use the natural logarithm and not have the log 2's floating around. At any time, however, all we have to do is divide whatever answer we've got in nats by the natural log of 2, and that'll give us the same answer in units of bits. So we're going to use the chain rule, and we're going to calculate dH/dP because the chain rule tells us that's really the driving factor in dH/dt. So dH/dP is the derivative of this two outcome entropy. We get, by the product rule, the derivative of the first, and the product rule applied to the second. Notice we have a p times a 1 over p, and we have a 1 minus p times a negative 1 over 1 minus p. And therefore we get this expression with a minus 1 and a plus 1, and clearly those cancel, and we're left with negative log p plus the log of 1 minus p. So what we've shown is this derivative calculation is going to be of this form, the negative log p minus the log of 1 minus p quantity negated times dp dt. Of course, we can use property of logarithms to write this as negative log of p over 1 minus p times dp dt. The log of p over 1 minus p is known as the log odds for probability p. And in particular, we're saying that the log odds of p is the natural log of p over 1 minus p. But what is p over 1 minus p? If p is the probability of an event B occurring, then p over 1 minus p is the odds of B occurring. So let's look at this concept of odds. So suppose we have B is an event, something that could actually happen in a sample space. The complement is B prime. That's the set of outcomes that are not in B. And B prime is often referred to as simply not B. Now suppose we had n trials of some experiment. And remember here, n is very large. If we expect Pn occurrences of B and Qn occurrences of B prime, then we say that the odds of B is P to Q. So an odds of P to Q means that B is P over Q times more likely to occur than B prime. A lot of times we simply write it as a R to 1 ratio, and therefore if a trial is R times more likely to produce an outcome in B as it is in B prime, then that's the odds of B. So suppose we toss a fair coin. B prime would be tails if B is heads. And if it's fair, then B has 1 to 1 odds. And a lot of times we say, well, that's a 50-50 chance. And notice those are the same odds, because 50 over 50 is the same as 1, which is the same odds-wise as 1 to 1. So the odds of an event B is the ratio of probability B to probability B prime, or we usually just write it as a fraction. So 3 to 1 odds means that the probability of B to the probability of B prime is 3 over 1, or the probability of B is 3 times the probability of B prime. And so B with 3 to 1 odds means the probability of B is 3/4, because the probabilities have to add up to 1. Now, we can write the odds, of course, in terms of the event B only, because the probability of B prime is 1 minus the probability of B. So the odds is the probability of B over 1 minus the probability of B. Notice that we can only define odds for the open interval 0 to 1. And if we let P be the probability of B, then the odds of B is P over 1 minus P. The log odds is simply the logarithm of the odds. So for instance, if P is a half, there's only 2 outcomes, true or false, and P is a half, then the odds of B is 1. That's a 1 to 1 odds. And the log odds of B is 0. And this is significant because the log odds B equals 0 is where the rate dH/dt is 0. And that's because it makes the dH/dP equal to 0. And we'll also see later on maximum entropy occurs or corresponds to the points where dH/dP is equal to 0. So our goal here was to make better decisions, to go from higher entropy, more uncertainty, to lower entropy, less uncertainty. And better decisions means making entropy decrease faster. Faster entropy means increasing the odds. So in summary, we have a strategy. Find a linear combination of features which causes entropy to decrease the fastest. In other words, we're going to write dH/dt is a linear combination of features, f1 to fn, with coefficients w1 up to wn. And we'll get something that looks like this. We have a w0 here, which is a constant. We'll discuss that later. And the result, when we put it all together, will be the logistic regression model that we'll look at very shortly. One note, often we call this natural log of P over 1 minus P. We often call that the logit of P. the odds ratio. We're going to look at another way of talking about this idea of a good decision based on dependence and independence, and once again, our key concept will be information. Suppose we have some very large number n of observations of an experiment. In other words, suppose we have big data. And suppose that we have two classes. We have the positives and the negatives. And suppose that each observation has some set of features, and features have properties. So for instance, the F sub beverage would be soda in the getting dessert data. And we have a question: if an unclassified observation has a feature F sub j with a given property, how much more or less likely is it to be in class 1 than class 0? Let's look at this question in a little more detail. Let's look at the who's getting dessert. That was data for 111 restaurant patrons. And we had features. And our class was getting dessert. And so we'll have y equals 1 if they did get dessert, and y equals 0 if they did not. And notice that we subscripted earlier the features with the actual names of the features. So for instance, if we were looking at F sub